Hi everyone. Today we're going to continue chapter 4 and we're going to go over Lewis structures for covalent molecules. So there are a few steps we need to follow when we're drawing Lewis structures. The first step, we want to use the molecular formula to determine how many atoms of each type are in the molecule. Now remember that in covalent molecules, we'll have non-metals. So maybe we have something like CO2. So this would tell us that we have 1 carbon and 2 oxygens. In the next step, we're going to use the given connecting pattern of atoms to draw an initial structure for the molecule. So usually what we'll do in this step is identify the atom that can make the most bonds, and that will go in the middle. So for CO2, if we draw the Lewis symbols for carbon and oxygen, carbon has 4 valence electrons because it's in group 4A, and each of those 4 electrons are unbonded, or they're single electrons. So they have the potential to pair up with electrons from another atom. So carbon can make 4 bonds. And then oxygen is in group 6A, so it has 6 valence electrons. And only 2 of its electrons are unpaired, so those 2 electrons are available for bonding. So oxygen can only make 2 bonds. So that means that carbon will go in the middle of the molecule. So maybe we would start by drawing carbon, so I'll just draw that up above, with 2 oxygens, 1 on each side. Another thing that's really useful for this step is just knowing that molecules like to be symmetrical if they can. So those 2 oxygens would want to be on either side of the carbon. Now in step 3, determine the total number of valence shell electrons contained in the atoms of the molecule. So we said carbon has 4 valence electrons, which I'll abbreviate VE. And then each oxygen has 6 valence electrons. So I'm just going to multiply 6 by 2. Oh, I wrote plus instead of multiply. So this would give us, let's see, 6 times 2 is 12, plus 4 is 16 total valence electrons. Now the reason that we want to determine the total number of valence electrons for this molecule is so that we can determine where those electrons will go in the molecule itself. So will the electrons be used for bonding, or will they just be lone pairs hanging out on a particular atom? All right, now this slide has a lot of words, but we'll walk through it. So in step 4, we're going to put 1 pair of electrons between each bonded pair of atoms in the initial structure that we drew in step 2. So for instance, with carbon dioxide, we said that there would be an oxygen on each side of carbon. And then we're going to put 1 pair of electrons between each set of atoms. So those will be our bonds. And remember that those electrons are being shared, so those will be covalent bonds. All right. Now we're also going to subtract the number of electrons that we used to make our bonds from the total number determined in step 3. So we said that we had 16 total valence electrons, and we just used 4 electrons, so 1, 2, 3, 4, to make our bonds. Oop, jumped ahead. All right, so we'll subtract 4 from 16, and that tells us that we have 12 valence electrons left. And we're going to use those remaining electrons to complete the octets of all other atoms in the structure, beginning with the atoms that are present in greatest number in the molecule. So remember, the octet rule tells us that every atom wants to have 8 valence electrons, or it wants to become like a noble gas. And we're going to start by giving each of the oxygens 8 electrons. So let's add some lone pairs to each oxygen so that they each have 8 total electrons. Okay, so the oxygen on the left has 8 electrons. The oxygen on the right has 8 electrons. And that means that we have used, let's see, 2, 4, 6, 8, 10, 12, 14, 16 electrons. So we used up all of our valence electrons. Now, one exception to that octet rule is hydrogen. So remember, hydrogen atoms only require 1 pair of electrons to achieve the electronic configuration of helium. So while the majority of atoms would love 8 electrons, hydrogen is our exception. Now in step 5, if all octets cannot be satisfied with the available electrons, we can move the pairs of electrons, or the non-bonding pairs, to positions between atoms to complete octets. And this will create double or triple bonds. So for instance, in CO2 above, even though both oxygens have 8 electrons, carbon does not. Carbon only has 4. So if we draw kind of a circle around carbon and its shared electrons, there's only 4 there. So one thing that we can do, let's see if I can carefully erase this circle. We can move some electrons around in order to give carbon 8 electrons. And remember that I said earlier, molecules like to be symmetrical if they can. So what we can do, and let me choose a different color here, we can move these non-bonding electrons down in between the atoms. So electrons are pretty mobile. Remember, they're pretty energetic and they like to move around really quickly. So they can be moved around. So now carbon is sharing 4 electrons with the oxygen on the right, and it's sharing 4 electrons with the oxygen on the left. So now carbon has a total of 8 electrons. Now, even though we moved those pairs of electrons from oxygen, oxygen is still sharing those electrons. So each oxygen still has 8 electrons as well. So if we draw circles around what each oxygen owns or co-owns, we can see that each oxygen has 8 electrons. So 2, 4, 6, 8, 2, 4, 6, 8. And then carbon also has 8 electrons. So now all of the octets are satisfied. And what we find is that carbon dioxide has 2 double bonds. So remember, we can also draw bonds as lines. So we could draw 2 lines in between carbon and each oxygen. And then we'll just add those non-bonding pairs of electrons, or sometimes we call them lone pairs of electrons, on each oxygen. All right, so we have 2 double bonds there for carbon dioxide. So really the main thing to remember is we're trying to achieve an octet for each atom. So let's go over an example. This time we're going to draw the Lewis structure for SO3. Now remember, if we're naming covalent compounds, we start with the first nonmetal, which is sulfur, and then we follow that with the second nonmetal, but we're only using the base name and then adding IDE. So we have oxide, and then we also want to add a prefix to our nonmetals if there's more than one. So for oxide, there are 3, so it would be trioxide. Now we don't add a prefix to sulfur because it's by itself and it's the first nonmetal. So if you have a molecule where the first nonmetal is by itself, we just leave out the prefix. All right, so this is sulfur trioxide. And the formula indicates that we have 1 sulfur and 3 oxygen atoms. So let's go through and figure out which atom should be in the middle. Now, sulfur is in group 6 and has 6 valence electrons. Oxygen is also in group 6 and has 6 valence electrons. So how do we choose which one goes in the middle? So another way to figure it out is whichever element is by itself, that will go in the middle. So we're going to put sulfur in the middle. All right, so we're going to put sulfur in the middle and then surround it with oxygen atoms. So this is kind of our starting structure. All right, and then we're going to figure out the total number of valence electrons. So each atom here has 6 valence electrons. So we're just going to multiply 6 by 4. Oh, my pen is not working. There we go. That's so strange that it does that. Okay, so again, we have 4 atoms, each with 6 valence electrons. So that gives us 24 total valence electrons that we can use to make our molecule. All right, so now we're going to place 1 pair of electrons between each oxygen atom and sulfur. So we're making our bonds. And I guess maybe I should draw this pair sideways so it makes a little more sense. So I'll draw this one sideways. There we go. Okay, so let's subtract. So we use 2, 4, 6 electrons. So let's subtract 6 from 24, and that will tell us how many electrons we have left to play with. So we have 18 valence electrons left. And we want to make sure that everything has an octet. All right, so let's put those electrons on oxygen. So we're going to give each oxygen an octet. Okay, so each oxygen now has 8 valence electrons. And now let's count and see how many electrons we've used. So starting with the oxygen on the left, we have 2, 4, 6, 8. We'll jump to the oxygen on the bottom. 10, 12, 14, 16. and then the oxygen on the right, 18, 20, 22, 24. Okay, so we used up all of our electrons, and you'll notice that the 18 electrons we had left were placed around each oxygen to give them octets. But sulfur only has 6 electrons. So if we draw a circle around sulfur, there's only 6. So we're going to need to move some electrons around in order for sulfur to have an octet. So I'm just going to pick one of these oxygens at random because we could take electrons from any of those oxygens. They're all pretty much the same. So I'll just move a pair of electrons down from the oxygen on the right. All right, so now, change my pen color. So now we'll have 4 electrons that are shared between the oxygen on the right and sulfur. And the other 2 oxygens will just stay the same. So that means that we actually have a double bond between sulfur and the oxygen on the right. And those lone pairs can be moved around. They could be on the top or the side or the bottom, just as long as there's 2 lone pairs of electrons there. And then I'm also going to draw lines for the other bonds as well, so that you can kind of see what that looks like. And if you're more comfortable with drawing dots instead of lines, that's okay with me. I'll still know what you're referring to. All right, so now sulfur has 8 electrons, and each of the oxygens have 8 electrons. So this is our final Lewis structure. Now, if a non-bonding pair of electrons from either of the other 2 oxygen atoms is used, the following structures result. So we could have had a double bond between the oxygen on the left and sulfur, or we could have had a double bond between the oxygen on the bottom and sulfur. So there are 3 acceptable structures for SO3, and all of these are correct. Really what matters is that there are 8 valence electrons around each of the atoms. Now, what about polyatomic ions? Remember previously I told you that polyatomic ions are a group of atoms that carry a charge. And in fact, polyatomic ions are covalently bonded groups of atoms that carry an overall electrical charge. We also said that most common polyatomic ions are negatively charged. So if we want to draw a Lewis structure for a polyatomic ion, we're going to use the same steps that were shown earlier, but there's one change. In step 3, 1 electron is added to the total number of valence electrons for each negative charge on the polyatomic ion. And 1 electron is subtracted from the total for each positive charge found. And then all of the other steps will be the same. So let's actually look at a couple of examples to kind of see what that means. So let's draw the Lewis structure for the ammonium ion, NH4+, and then we'll do the same thing for the nitrate ion. And remember that you should know the names for the polyatomic ions, and I did post some flashcards last week with the names and the formulas for all of the polyatomic ions that I expect you to know. All right, so starting with NH4, we have a nitrogen and 4 hydrogens. So each hydrogen only has one valence electron because it's in group 1. So it can only make one bond, whereas nitrogen has 5 valence electrons and 3 of them are unpaired. So nitrogen can make 3 bonds potentially, and actually it can make more than that, which we'll see in a second. So nitrogen should go in the middle for this particular structure. But also, I mentioned that whichever atom is by itself will go in the middle, and nitrogen is by itself. So we'll put nitrogen in the middle, and then we'll surround it with the 4 hydrogens. Okay, so now we want to determine how many total valence electrons we have. So we just said that nitrogen has 5 valence electrons. And then we said that each hydrogen has 1 valence electron. So we'll just multiply that by 4 since we have 4 hydrogens. And now we want to take the positive charge into account. Now that positive charge tells us we're missing an electron. So we're going to subtract 1 electron because we lost it somewhere along the way. So that minus 1 valence electron will take into account that positive charge. So that will tell us that we have, let's see, 5 plus 4 minus 1. So that will be 8 valence electrons. Okay, now the next step is to put 2 electrons in between each pairs of atoms. All right, and we actually used up all of our electrons. We've got 2, 4, 6, 8. Nitrogen has 8 electrons, which makes it happy. So it has an octet. And remember, each hydrogen only needs 2 electrons to become like a noble gas, because the nearest noble gas is helium, and helium only has 2 valence electrons. So all of those hydrogens are happy as well. Now, we do need to indicate that there is a positive charge on this polyatomic ion. So what we'll do is add brackets around the structure and then put a little positive charge at the top right. Okay, so now let's look at the nitrate ion. All right, so nitrogen is by itself, so it will go in the middle. And then there are 3 oxygens, so we'll put those 3 oxygens around nitrogen. So this kind of looks like SO3 so far. So now we want to calculate the total number of valence electrons. So again, nitrogen has 5 valence electrons. And then each oxygen has 6. So we'll multiply 6 by 3 since we have 3 oxygens. And now we have to take into account that negative charge on nitrate. So it's a -1 charge, which means we have an extra electron somewhere. So we're going to add 1 valence electron to our formula here. All right, so 6 times 3 is 18. And then we're adding 5, so that's 23. And then we're adding 1 more, which is 24 valence electrons. All right, so now let's put 2 electrons in between each pair of atoms. So we're creating our bonds. All right, and now we want to give an octet to each of the oxygen atoms. But first, let's figure out how many electrons we have left. So we just used 6 electrons to create our bonds. So 24 minus 6, we have 18 electrons left. Okay, so let's give an octet to each oxygen. Okay, so we used up our 18 electrons there. All right, so is every atom happy? Does every atom have 8 electrons? Nope. Nitrogen only has 6 electrons, so we need to add 2 more electrons, or share 2 more electrons. So very similar to SO3, we're going to move one pair of electrons down in order to make a double bond. So I'm just going to erase this pair and move it down in between oxygen and nitrogen. Okay, so now we have a double bond between nitrogen and oxygen. And also similar to SO3, we could have our double bond between the oxygen on the left and nitrogen, or between the oxygen on the bottom and nitrogen. So all of them are equivalent. It doesn't really matter where you put the double bond. And then the last thing we'll do is add some brackets and a negative charge in the upper right to show that this is a polyatomic ion. Okay, so I'm going to post a worksheet with some Lewis structure example problems, and that way you'll get some practice with drawing Lewis structures for molecules and polyatomic ions. And then I'll also post the key so you can double check and make sure that you got the same answer. In the next video, we'll talk about shapes of molecules. So we'll talk about something called the Vesper theory. All right, so I'll see you in the next video.